Hello everyone. So today I'm going to talk about Lecture 7 or Chapter 6 in your textbook. So in this lecture, we're going to talk about error control techniques. Okay. So far we have covered the situation where there is a transmission, there is a transmitter, there is a receiver, and there is a link in between, and we are sending data using encoding and modulation techniques. All right, and we talked about errors several times over the last few lectures, right? And we saw sources of errors, noise, quantization, others as well. All right, so today we're going to talk about how to discover errors. Okay, so we cannot prevent some of the errors no matter what we do. So how can the receiver detect the errors? So at least it can, later we will see how the receiver can reject the errors and ask for retransmissions as a technique to recover from errors, right? But so for now, we need to talk about error detection techniques. So this is our topic today, and before we start, let's talk about types of errors. So when we talk about errors, we really talk about flipping of a bit, because all the information that we are sending is about ones and zeros. All information we're sending are ones and zeros. So when we say an error, what I mean, we're not getting half one or half zero, right? So what will happen is the receiver misinterprets the information that's coming. So instead of receiving a 1, it receives 0, or if it's receiving 0, instead of receiving 0, it receives 1. So that's what we mean by the errors. Okay? Instead of reading 1, it reads 0, and vice versa. If these errors are few and far in between, we'll call them single bit error. So bit changes here and bit changes there. They are a single bit error. They may affect one stream of bits, and that's it. But these single bit errors are not the common type. Right? If there is noise happening in the channel, most likely it's gonna affect multiple errors, right? So we'll call those burst of errors, right? Or error burst. So in your slide here, it shows to the right side a single bit error, which is a bit that's isolated from everything else. While to the left side, we see a burst. A burst can affect multiple errors in a close proximity to each other. So it may, as you can see here, there are two bits, adjacent bits, that are affected. They are flipped from 0 to 1 and from 1 to 0, right? But also, if we see a close errors that happen close to each other, even though there are some bits in between that are not affected, we're still call this a burst. So here we have one that's flipped to 0, then we have two bits that are not affected, then two bits are affected, then two bits are not affected, and so on. So the whole group is called a burst, right? So burst doesn't mean that all the bits are affected, but a lot of bits that are close by are affected and flipped. So these are the kinds of error that actually a little bit harder to detect a single bit could be easy, and we will see some techniques that can easily detect single bit errors. More sophisticated techniques are needed to deal with burst errors. So before we continue, I want to explain something that's like how we detect errors. So I'm gonna switch to my notes here, and I want to explain what is the principle behind all the error techniques, error detection techniques. There is one principle behind all of them. To explain that, let's assume that the sender, the transmitter here, and the receiver know a language. Both understand one language. And the language, conveniently enough, consists of four letters, four words. Let's say four words: A, B, C, and D. Any conversation between the transmitter and the receiver includes only A, B, C, and D. And this is what's not far from what we know, because all the transmitter and the receiver have actually two letters, not four, two letters that make up all the words, which are the 0 and 1. All right. Now, if the communication channel is noisy, the A, B, C, and D may get corrupted and get to the other side in a different form. So let's say A is transmitted, right? And what is received is B. Now the receiver doesn't know what the transmitter has sent originally, but B is a valid word. So the receiver has no idea that there was an error happened, and it will receive B as a word, as a legitimate word. Same thing if the transmitter sends D and it get corrupted and it's received also as B, the receiver simply thinks that the transmitter sent B twice. Right? So the solution here is to actually have more words in the language between the transmitter and the receiver. And why we have more words? So that we can have some legitimate words and some words that are not valid, right? So let's assume that actually the transmitter and receiver use a language that has, let's add more words. So A, B, C, D, E, F, G, H. So we added 4 more words. But we decided that the only legitimate and valid words are the first 4, and the other words are not legitimate. So if the receiver receives any of the other letters, it will consider them as errors and it will not accept them. So now, if the transmitter sends A and it get corrupted and became E, the receiver says E is not legitimate. This must be an error. Okay? If C is sent and it was received as H, the receiver will reject it. Okay, so now we have a way to detect errors by having a vocabulary that's actually bigger than the useful vocabulary or the valid vocabulary, so that there may be a situation where the valid word changes to invalid word, so the receiver will detect the error. Is this good technique? Well, not really, um, because we may have a situation where A is sent and B is received, and the receiver sees B as a legitimate word, so it says, great, it must be there must be no error in the channel, and because I received B, which is a valid word. All right. So in this case, I may still, using this technique, I may still have errors, but the ability to detect errors became better. Before, there was no way to detect errors because every legitimate word is changed to another legitimate word. When I added these other invalid words, I increased my ability to detect errors, because in some cases the legitimate word changes to invalid word, so I can detect the errors. But still, if you look at it, there is still 50% chance that uh, I don't detect the errors, right? And that's the basic idea behind all our error detection techniques. We increase the vocabulary that we use so that when we have errors, or so that when a valid word changes to invalid word, we detect it. But in all of the techniques that we will see, there is a possibility that a valid word changes to another valid word and we won't be able to detect errors. So there is an error detection efficiency here. Right. Okay, so let's look at the first technique that we have and we see how we implement this principle. So the first and simplest technique we have is something called a parity bit. So in a parity bit, we add additional bit to the original number of bits. So if we have um, in these examples, if we have 6 bits, we add a 7th bit, and that 7th bit will be our what we call our parity bit. How do we add the bit? All right, so we can add it so that the number of ones are always odd, or we can add a bit so that we can make sure that the number of bits are always even. All right, so let's see. Let's assume that we are trying to send these sequence of bits. So this corresponds to our valid word. I mean. Right? And now let's add another bit so we can make the number of ones even. So we have 1, 2, 3 ones. If we add another bit here, the number of bits become even, so it's 4. And we send this. If the receiver receives 1100101, right? It adds the number of ones, so 1, 2, 3, 4. It finds them even, so it says, well, this is a valid word and everything is okay, no error happens. If an error happens somewhere, let's say here. So what we are receiving is 1000101. So the receiver will count the number of the number of ones and find it odd. So it says, well, we must have an error here because we're not supposed to receive an odd number of ones. The error can happen anywhere, including the parity bit itself. So we may receive something like 11000100, right? So here the actual number of the actual bits, there are no errors in them. The error happened in the parity bit. It's still, the receiver will count the number of ones, find it odd, will say this word is invalid and there is an error. So here, as I said, the principle was to have more words than the actual vocabulary. Our vocabulary consists of 6 bits. So from 0000 to 111111, or 6 bits. That's the actual valid words that both the receiver and the transmitter wants to handle. We are adding a bit to this. So instead of having 2 to the power 6, that's, what is it, 64 valid words, we are using 2 to the power 7, so we're using 128. So now we doubled the amount of words that we have. Half of these words are invalid. Which half is the half that has odd number of ones? If we use even parity, then all the words that have odd ones are invalid. Does this technique handle all errors? No. As I said before, we may end up with a valid word or a valid word that's corrupted and end up changed to another valid word. So let's consider the example where we have 2 errors. So now error happened here and error happened here, or let's say happened in these 2, right? So you don't always think that the error happened at once. So now the receiver will receive 1, the other one flipped to 0, 0, then the 0 flipped to 1, then 1, 0, then 1. Now the receiver adds the number of ones, it finds it even. So it says, hey, this is a valid word. While in fact, it's not, because we have 2 errors. So this technique handles or detects all odd number of errors, and it cannot handle the even number of errors. That's the weakness of this technique. Simple technique, but its weakness is it cannot handle even number of errors. So if we assume that the number of errors can be even or odd, 50-50, so this technique may not handle 50% of the errors, right? All right, so let's see how we can improve upon this technique. How about we arrange blocks of these words into 2-dimensional matrix, right? So we take sequence of them and we arrange them as a matrix, and then we add a parity in 2 ways, horizontally and vertically. So we need to create a 2-dimensional parity scheme. So the example at the top here, so the example here at the top, uh, shows the original bits B1, B2, B3, B4 up to Bj, which could be any number, right? Maybe 6 bits, maybe 7 bits. And we can add the parity horizontally as we did before. So if it's an even parity, we can add the number of ones, then we add a 1 or 0 to make the number of ones even. We do the same thing vertically as well. So we add the number of ones vertically, and then we add a 1 or 0, depends on whether it's parity or even parity or odd parity. So here is an example. So we have in this row 3 ones, so we add 1 to make them even. Same here, same. So all rows happen to be needed 1. Vertically, the first column has zeros. So you can see here my cursor. The first column has all zeros. So we add 0 to make the number of ones even. Here we have 4 ones, so we add 0. 2 ones, we add 0. 3 ones, we add 1. And there is a 1 here, so we add another 1. So in all cases, we have even number of ones. Now, if an error happens, and it's a single error, it will be detected by both rows and columns. Why? Well, if we count the number of ones here, we find them odd, 3 ones. We're supposed to have even number of ones, so we detect an error. And we also detected vertically as well. So it's great for single errors, same as before, we can detect it. For double errors, so see here in the left bottom, so we have 1 here that is flipped, and we have another 1. So we have 2 errors. If we actually, this example is different than the top examples here, so it's a different example. So if we count horizontally, so 1, 2, 3, 4, right? 4 ones. 4 ones is still an even number, so we cannot detect it horizontally. How about vertically? Vertically, 1, 2, 3, 4. Still, we don't detect the error. So, in fact, this is a problem that even in this two-dimensional technique, we may get a situation where we don't detect the errors. But let me, before we do that, this example is actually undetectable, uncorrectable errors, even with the double matrix, or with the not the double matrix, with the matrix. Let's see a way that actually this works. So let's have a matrix like this: 1, 1, 0, 0. Right, so we have this example, and we need to create the parity horizontally and vertically. So here we have to add 0 because we have even number of ones. Here we need to add 1, and another 0 here, and 1. So it's even ones in all the rows. Vertically, we have to add 1 here, we add 0 here, we add 0 here, and we add 1 here, right? So now we send this. Let's assume that errors happen, and to show an error, I'm just gonna circle this, or use actually red. So instead of the 1, which is the correct number in black, we receive 0. So now the receiver will be able to detect the error because it counts the number of ones, it finds it odd, right? Now before, let's create this, let's assume that we have 1 here. So we have 2 errors. So if we rely on the horizontal parity bit alone, we will see that we have 1, 2, 3, 4 ones. That's an even number of ones, so we say this is correct. But if we look at it vertically, we will see that this is okay. This is not okay because we have 3 ones and we're not supposed to have 3 ones. So we know that there is an error. So with this matrix technique, we will be able to enhance our detection technique, error detection technique, by creating this matrix, and we will be able to detect some double errors, not all. Why not all? Well, if we go back to the example here, we'll see that we actually find the reason for this. So if we have unfortunate situation where there is 4 errors arranged in this perfect situation, we won't be able to detect them because it happens that we have 2 errors or even number of errors in the column and also even number of errors in the row, so we won't be able to detect them. So the point here is, even with this 2-dimensional parity scheme, we still have some errors that go undetected. Okay, but it's still overall an improvement. Okay, the other technique that we have is actually a simpler one, but even probably even less efficient. So these are used, this technique is used in the internet headers, and it is used to quickly check whether the internet header is valid or not. And the idea is simple. The idea is to treat the bytes in the header as numbers and add them using one's complement addition, right? So one's complement addition, for those who remember or forgot, if we have a carry here, the bit carry, we add it back, so we end up always with the same number of bits. So we start with 8 bits, we always end up with 8 bits, no matter how many times we add, right? So the idea is we take numbers. Let's say our header has number 9, 8, 7, 1, 5, 4, right? Any numbers. So what we do is add 9 plus 8, we get 17, plus 7, 17 plus 7 is 23. Probably I'm not very good at doing calculations in my head, so I'm just going to use my calculator here on the side. So 9 plus 8 plus 7 plus 1 plus 5 plus 4 . Oh, we end up with 34. So we add 34 here and we send the packet. So the receiver will do the same thing, right? We'll add the numbers 9 plus 8 plus 7 plus 1 plus 5 plus 4. And if the result is 34, then the packet is correct and no error happens. If it receives something different, then there must be an error in the packet. Now you can see that this is not a very solid technique, simply because there may be error happening. Let's say what the receiver received is 9852 or 5354. So if I add these numbers together, I'll end up with a 34, even though actually two errors happened. This was decreased by 2 and this was increased by 2. Right? So obviously this is not a perfect technique, but it is a very easy one to implement and use. So now, instead of handling this in decimal, as I showed you, decimal is easy to do, but instead we'll use hexadecimal to do the calculations, right? So with the hexadecimals, now we have the numbers from 0 to F, right? F is 15, 0 is 0, right? So if we have a sequence like 001, F203, and so we can add the numbers together, we get F204. We add it, so the sum from the first 2 bytes, or the first 16 bits, actually 16 bits. So 0001 represents a 16 bit, right? We add it to F203, that's another 16 bit. We end up with F204. And then F204, we add it to the next 16 bit, F4, F5. We end up with 1E6F9. We do the carry, so we take the 1 from here and add it to the 9, so we get A. And we continue doing this until we get DDF2 at the end. If we flip the ones to zeros and the zeros to 1, we do something called 1 complement. So this, the 220D is the 1 complement of the DDF2. And this is actually what we add in to the packet, right? So we add the one's complement. The receiver will do exactly the same thing. We'll add, and you see here that the results are the same when you compare the two columns. We continue doing this. The last step, we actually add the complement, the one's complement. We get FFFF. The reason for doing that is, instead of comparison, right, we do this so that if the receiver sees 11111, which is the FFFF, it says, or it figures out that there is no error. If anything other than 4 Fs is received, then the receiver will detect an error. Will say, well, I didn't get all ones. There must be an error there, right? So this technique requires a little bit of practice. So maybe you can take this example and any other example in the book, and you add them together patiently, step by step, and you do the both sides. You do the original addition, and then you do the addition again, and you see if there is no error, you should get FFFF. If you introduce any error, let's say if this byte here, or the sequence here, instead of E6FA, you get something else, then obviously the result will not be the same. You will not get FFFF at the end. Okay, the final technique we see, actually there is more technique we'll see later, but the final technique for the error detection only is called the cyclic redundancy check, which is the most sophisticated and the most robust among the techniques that we are studying in this course. So the idea here is we take a number, divide it by another number, and we send the remainder, right? So let's say take a number 9 divided by 4. Now 9 is not divisible by 4, so we have a remainder of 1, right? 9 divided by 4 is 2, and the remainder is 1. So we send the 9 and we send the 1. The receiver does the same thing, divide 9 by 4, and gets the remainder. If the remainder and the remainder are equal, say, okay, great, there's no error. If the 9 changes and become 8, the receiver divides by 4, you get 2, and the remainder is 0. The remainders do not match, then there must be an error. So that's using it, or using a decimal in example, which is not great example, but illustrates the whole the idea. It actually works better when we look at binary, and we do binary operations. Okay? So the technique is robust because it works better handling binary numbers. And the idea behind it is to look at the binary numbers as polynomials. And we'll deal with this technique both as a binary sequence and also as polynomials, but the idea is the same for both. To understand this technique, we have to look at some principles. One of them is modular 2 arithmetic. So modular 2 arithmetic is, as I said, in decimals, if I divide 9 by 2, there is a remainder, right? The remainder, or divide 9 by 4, the remainder is 1, right? So the modular is looking for the remainder. So if I say 9 divided by 2, again, the remainder is 1. When I divide 9 by 2, I get 4, the result, and we have 1 is the remainder. So modular 2 arithmetic is division by 2, taking the remainder, right? And this is exactly the result of the XOR operation. So XOR operation, we love it because it does a lot of useful things for us. Another useful technique for, or another property, nice property for the XOR is that the addition and subtraction are the same. They give me the same result. So 1 plus 0 gives us 1. 1 plus 1 gives us 2. But if I do modular arithmetic, so 2 divided by 2 is 0. 2 divided by 2, the remainder is 0. So I get the remainder 0 here. 1 plus 0 is 1. 1 plus 1 is 0. Right? And the same thing in the subtraction. So ignore the addition and subtraction, just look at it as XOR operation. So the XOR operation, if the two operands are different, we get 1. If the two are the same, we get 0. So 1 XOR 0 is 1, 1 XOR 1 is 0. I'm probably explaining it too much confuses you more than it helps, but just the idea that we need to think later about it in terms of subtraction and addition. Same thing with multiplication. So if I multiply 11 by 11001, we get, multiply it as you do normal multiplication. So the 1 multiplied by 10001 gets us the same number. When I multiply by the other one, we'll get 110010, and then we add, we get this number. Right. So, okay, now this is a little bit of math. Let's take a look at how we can use what we, or let's take a look at just the bigger picture right now before we get into the details. So we have a sequence. We are trying to send a sequence a sequence of bits. So the sequence of bits could be anything, right? And this is our message. We'll call this M. And before we send it, remember all these techniques that we talked about, we're adding more bits to the message, right? So in the even parity, we took 6 bits and added 1 bit to them. In the checksum, we added another 16 bit, so to the sequence of to the header, we added another number, right? So we're always adding something before we're sending it. This is no different. We're adding something. So we will add something here. We'll call it F. What is F? F is the result of dividing the message M by a specific polynomial. Let me sneak a peek here at, we'll call the polynomial P. Okay, so just to make sure that I'm using the same terminology. So we need to divide M by P, right? So when we divide two numbers, we get the quotient and the remainder. So as I said before, if I divide 9 by 4, we get 2, right? Plus 1 over 9. Or elementary school students do this all the time. Or actually even junior high students. So 9 divided by 4, we get 2 and 1 over 9. And this is the remainder. We'll take this remainder and put it here and send it. The remainder in 4, so because 9 is the number, so we just need to send this part. if you look at your slides, you will see that actually I missed a point. Small, not a small, well, it's very important, which is before I divide, I need to shift the number, or so I need to leave space for the f to be inserted. So you will see in your slides that we are actually doing n to the power nm divided by p. So what is this part? Where this part come from? Okay, so first of all, this multiplication here is a mathematical way to say we are shifting the bits. All right, so let me show you an example. Let's say I am multiplying 2 to the power 1, multiplying it by 1. So what we get is 2 multiplied by 1 is 1, 0, in binary, of course. If I say 2 to the power 2 multiplied by 1, that's a 4 in binary. 2 to the power 3 multiplied by 1, that's 8 in binary. So every time I am shifting by, here I'm shifting by 1, here I'm shifting by 2, here I'm shifting by 3. So when I do this, 2 to the power n multiplied by m, I am shifting m by n number of bits. So what is n? Here is the size of the remainder. So I am shifting m by certain number of bits that represent the size of the remainder. And then do the division. So when I do the division, I get quotient plus the remainder over p, right? And that's what we will push here. So at the end, what I will send is a message. So the message that I will send eventually, we'll call it T, and T is I'm using F and R, so which one the slides uses? Slide use the term F. But F here is the remainder. So this is what I will send to the receiver. The receiver will do the same thing. We'll take m, shift it, divided by a specific polynomial, specific number, and then actually the receiver will take the whole t and divide it by the polynomial. So the receiver will take m plus f divided by p, and you will go to the slides and see how this works. So the idea is, if the receiver receives if there is no error happening, the end result of division by the receiver will get 0, will get no remainder. If there is any error happened in any part of the message, any part of T, the receiver will get something different, will get a remainder, so it will detect the error. All right, so let's go back to the slides and see how this works. All right, so you will see here that we have our definitions. So T is the bit frame that needs to be transmitted. M is the original message, which let's say it has K bits. K is the number of bits. F is the number of bits that we need to add. Or actually, it is the FCS, or the cyclic redundancy check. And P is the pattern by which we divide. Right? So we create T, which is n to the power n, well, multiplied by m plus f, right? So I explained already the purpose behind 2 to the power n. So n is the size of the f. So what we need is to shift the message by n number of bits. So when we shift, we add zeros to the right side. Okay, so we're shifting them. So we're adding 0 to the right side, right? And then we create this t, which is the shifted m plus the f, right? So the math says if we take the shifted m and divide it by p, we get the quotient and we get a remainder. So we construct t by adding the remainder to the shifted message. And we call this frame check sequence, right? Which is exactly as the remainder. All right, so the receiver receives t, so it divides by p, and this is equivalent. So t, we already know that the t is the shifted m plus r. So now we take the shifted m plus r divided by p. This we know that will result in q plus r over p. So here, this is the q plus r over p. This part is the result of dividing 2 to the power n m divided by p. Then r plus r over p repeats again. This is the other part, which is the result of dividing r over p. Because we're dealing with XOR operations, anything that's added to itself is 0. So these two cancel each other, and what we get is quotient only. So the receiver, if they take t over p, they should not get a remainder. The remainder should be 0. They should get only quotient. So for no error, the remainder should be always 0 at the receiver side. If there is any error, this means that the m here changed, which means that the whole operation will not result in a 0 remainder. It will result in something else. So that's the idea behind the idea behind the CRC or the FCS. The CRC is the mathematical term. All right, so let's use an example, because there is nothing better than an example to illustrate. Right? So in this example, we have a message that has 10 bits. And we have a pattern that has 6 bits. And something that you need to kind of memorize is that the size of the remainder is always 1 bit less than the pattern. So if the pattern is 6 bits, then the size of the remainder is 5. So here the size of the remainder is 5. Okay, this is important to understand because when we shift the message, we want to shift it by 5 bits to the left. So when we shift the message, we multiply it by 2 to the power 5, which is practically means shifting it by 5 bits. So we'll see here the 10 bits, and then we added 5 bits to them, 5 zeros. All right, so this is the number that we need to divide. Okay. So we do a long division. So now I'm gonna repeat this to you manually so that you can look at it. Okay, let me see if I can memorize the numbers. So we have, oops, so our pattern here is 1 0 1 0 0 0 1 1 0 1, and then we add 5 zeros for the shift, right? And then our P, so this is the message, not the pattern. As I said, pattern is this actually the message, and this is the space we leave to add the remainder. The pattern by which we divide is we have 6 bits, so it's 1 1 0 1 0 1. Okay, so now we do a long division. Now everybody knows how to do long division a different way, so I'm gonna use the technique that I'm used to. So if I want to multiply, we need to, every time we need to do a division, we need to get rid of the leftmost significant bit here. So to get rid of this 1 here, what we need to do is multiply the pattern by 1. So we multiply by 1, we get 1 1 0 1 0 1, right? And we subtract using the XOR operation. So 1 minus 1 is 0, it disappears. 0 minus 1 is 1. So I'm gonna do this here. 1 1 0 1, and then when we have to take one of these bits and lower it so that the next step we multiply by 1 here, so we get 1 1 0 1 0 1. So this is 0, it's 1 1 1 0, and we lower one of these bits. So to get rid of this 0, we need to multiply by 0. We end up with all zeros. And if you are comfortable enough, you can skip this part altogether. But I'm gonna keep doing it. Right, now we multiply by 1 again, so that's 1, 1, 0, 1, 0, 1. So you see here that we end up with another 0 at the left side. So you have to be patient doing this and be careful not to make mistakes. And I made mistakes before, so keep an eye on what I'm doing. I may end up actually making a mistake. All right, so you see if you are following me. And don't have much to say here, so I'm gonna be quiet. I don't need to do the last step here. Or maybe I do. So we end up with 5 bits at the end, represent the remainder. Let's see if this is what, that's the remainder in the slides as well. All right. So I did everything correctly. So what we will send is the original message plus the 0110 at the end. Now, you see here that the number of steps in the slide are less. Why? Because we skipped the zeros. They didn't put the zeros. Every time we see a 0 here, we did the operation. So those lines are skipped in the slide. As I said, if you're comfortable, you can skip them. So every time you see 2 bits being eliminated, you just put 0 and continue, right? If you're not comfortable, just do it the way I did. Okay, so now we ended up with these 5 bits. This is the remainder. So what we will send is the original message plus R. So the original message, again, I'm just going to copy it from my notes here, is 1. Let's use the black ink. So 1, 0, 1 0 0 0 1 1 0 1. Okay, and we add the R. I'm gonna add them in a different color. So that's T. That's what we will send. Right? The receiver will do the same operation again using T. So the receiver will divide this by the pattern. So let's do the division, and we are expecting that there will be no remainder this time. Right? If there is a remainder, this means there is an error. If there is no remainder, means that there is no error. So I'm gonna do it exactly like this without any error. Right? So I'm gonna repeat the same long division again. Maybe I'll skip the steps this time. So 1 multiplied by the pattern will get the pattern. So subtract or XOR, same thing. Multiply by 1 again. 1 0 1 0 1. Now we're skipping, so I'm gonna use the shortcuts here. The quotient is not important, right? So if you make a mistake in the quotient, it doesn't matter. So you'll see here that I ended up with 5 zeros, right? Which means that there is no remainder, right? And that's because of the math we talked about earlier. All right, so I'm gonna do something that's not in the slides. I'm gonna create an error and see what happens. All right, so the receiver, if it receives a remainder of 0, means that there is no error. If anything else, if it receives anything else, that there must be something happened. So I'm gonna create an error somewhere in this message, and I'm gonna do the division again. So let's create an error here. So now if I want to do the long division again, I'm gonna multiply this by 1, so I get 1 1 0 1 0 1. multiply by 1 again, get 1, 1, 0, 1, 1. So we end up with actually a non-zero remainder, which means there is an error, right? So this is the example of both cases where we have an error and we don't have an error. All right, we see here that we can do the same thing using polynomials. So with the polynomial, I'm just going to explain how to convert the binary to a polynomial. Right? So the simplest thing to think about is if I go back to the pattern here, let's say this is the pattern 1, 1, 0, 1, 0, 1. Right? So let me clean it up a little bit. So 1, 1, 0, 1, 0, 1. This first one here corresponds to x to the power 0. The second bit corresponds to x to the power 1, and the third bit corresponds to the x to the power 2, and so on. And this is my polynomial here. You can, of course, put the plus sign in between. Now, obviously, the 1 and the 0 are the coefficients. So, because this is 0, then there is no x to the power 1 here term. X to the power 1 doesn't exist because it has a 0 multiplier here. Same thing with the x to the power 3 because it has a 0 coefficient here. So my polynomial that corresponds to the binary bits that I have shown you is p equal x to the power 5 plus x to the power 4 plus x to the power 2 plus x to the power 0. Okay? So you can convert any number to a polynomial using the same approach. If you were given a bit pattern like 1 0 1 0 0 0 1 1 0 1, which is our original data pattern, you could say This corresponds to x to the power 0 plus this doesn't exist here. This is x to the power 2, x to the power 3, x to the power 4 does not exist, power 5 does not exist, power 6 does not exist, power 7 exists, 8 does not, 9 exists. So this is our data. If we shift it by 5, means that x to the power 0 becomes x to the power 5, this becomes x to the power 7, and so on, right? So when you look at the PowerPoint, you see here x to the power 5, x to the power 7, x to the power 8, 12, and 14, because we shifted everything to the right, to the left by 5 steps. Obviously, x to the power 0 can be written also as 1, right? So you'll see the pattern here, x to the power 1 instead of x to the power 0, right? So here, 1, 2, 4, 5, and here, this is my pattern, 1, 2, 4, 5. 1, 2, 4, 5 at the top. And I can do the division just because we leave spaces. So I may do this in another recording because it's time consuming a little bit. But I can arrange my data as polynomial, and then I can do the same thing. To get rid of x to the power 14, so I have to multiply x5 by something. So x to the power 9 multiplied by x to the power 5, 9 and 5 adds up, so we end up with x to the power 14. So we'll put x to the power 14 here, and then we subtract them so we cancel each other. So that's the same operation using polynomial instead of binary. Yeah. So that's the end of the calculations on the example. We may take some examples later. But as I said earlier, this approach is the most robust among all the techniques that we saw, and it's the most mathematically sound as well. So how is it different than the others? Well, first, it detects all single bit errors. So all single bit errors in the message will be detected. It also detects all double bit errors as long as the polynomial has at least 3 ones, right? So in our case, our polynomial has 4 ones. So great, means that it detects all double bit errors. Also detect any odd number of errors as long as the polynomial contains a factor x plus 1. So if we factor this polynomial, we may find that we can multiply it by x. So it will detect all odd numbers. Any burst error for which the length of the burst is less than the length of the divisor polynomial. Right? So what's the length of the divisor polynomial? It's 5 bits. So any bursts that are less than or equal 5 bits will be detected. And also most large burst errors, so even the larger burst errors can be detected as well. Not all of them, but some. So there are many polynomials. We saw one example. That one example actually it's small, just for illustration. But we can have 12-bit polynomial. We can have 16. We can have 32. And the 32 is used for the Ethernet packets. So the CRC32 you see here from x to the power 0 to x to the power 32, and we can use it. If you think about it, any burst error for which the length of the burst is less than the length of the divisor polynomial. This means that this CRC32 can detect bursts up to 32 bits. Oh, great, right? The final thing that we need to cover is the circuit. Now, we don't do divisions actually in the packet when it's actually done by hardware, much easier done by hardware than doing polynomial division. And the circuit is actually very simple to understand. There are two circuits in the slides. This one from older versions of the book, and this one is the newer version that exists in the 10th edition. I'll explain this first, and then I'll show you how to design it in a simpler way. So the idea is, rather than do this using CPU or using the computations, we can do it using simple shift register and inline. So while the packet is being transmitted. So while the packet, when we prepare the packet, if you see later the frame, the Ethernet frame has the CRC check at the end, at the end of the frame. So we have the headers, we have the content, everything, and then the CRC comes at the end. So we can design a circuit, and actually network cards have this circuit that takes the bits from the upper layers, from the data link layer, and start sending them one by one. So when we are sending the actual bits, we're flipping the switch 1 here at the top, we're flipping it to position A. And then we keep sending the packets one by one, right? While actually passing the packets through this registers. So we see that the packets are going to the register C0, C1, C2, C3, C4, and so on, right? And every time we send a single bit, the content of these registers change, right? When we finish sending all the bits from the data, we switch to position B on the switch. And that time, the actual CRC becomes ready, and the content of the registers here is the CRC. So we start passing the content of the registers to the output, which means we are sending the CRC. So this is the register or the circuit that does the calculations for us. So it doesn't need complex calculations, just shift register and XOR operations. Okay, so I may leave the actual steps here for some other time, and there is an easy way to understand them rather than doing this slide. But I want to show you how to design the shift registers. Okay, so we will start by looking at my original polynomial here. Let's delete all of this. All right, so the technique is simple. You have your bits. This is the polynomial. I will put a register between every 2 bits, right? So between every 2 bits, put a register. Because we have 6 bits, we need 5 registers. And remember, I said the remainder size is 1 bit less than a polynomial size, right? So this is register C0, C1, C2, C3, C4, 5 registers, right? And then I need to create an XOR operation every time I see a 1. So there is an XOR operation here. There is an XOR operation here. No, there is no XOR operation here. There is XOR operation here and an XOR operation here, right? You can add an XOR operation here as well, but it's useless. So you can put an XOR operation every time there is a 1 except the last. Then you can connect all the pieces together and then connect the last register with the first register and also with the middle registers. And that will be your circuit, right? Every semester the students are asking me about repeating this many times, and so I'm gonna repeat it again. Although this is probably the least useful information in this course because nobody's ever gonna ask you to design a circuit like this. But it's in the book. So you create a register between every 2 bits. You will end up with number of registers 1 less than the number of bits. And then you create an XOR. Every time you see a 1, you put an XOR below it, except the last one. If you made a mistake and add it, that's fine. It's not gonna add any. It's not gonna change anything. And then you connect the last register with all the XORs, and you connect the XORs with the registers. You end up with the circuit. Now there is a slight difference between the 2 circuits that you see here. The difference is just because we are entering you see the XOR here. Instead of putting it in front of C0, we are putting it here, but it's the same effect, right? If you compare my circuit that I showed you to the circuit here, you'll find they are the same, right? Okay, so that concludes the lecture today, and I will see you in the next lecture.